We saw when working with fluids that pressure times volume has units of energy. And it turns out that the work done by a gas at constant pressure is minus P delta V. Now let's talk about that for a moment. Why the minus sign? If I have a gas trapped in a cylinder and I expand that gas has to push against the air in order to move, right? This piston here is doing work. Well, doing work against the environment means that it's expending energy to do that. And the way we account for energy when we're dealing with gases in enclosed systems is by taking anything that adds energy to the gas and make that positive, and anything that removes energy from the gas and make that negative. So when you do P delta V, if delta V is positive, that negative sign in the front of it makes the work negative. Whereas if the environment pushes on the cylinder and compresses the gas, it does work, it adds energy to the gas, it'll actually heat it up. And adding energy to the gas then is positive. So a negative delta V results in a positive work. You can actually find this fact as point 2 on the bottom of the front page of your reference tables. When we are talking about gases and the behavior of gases and gas engines, it is very, very common to make use of something called a PV diagram. A PV diagram is a graph of all the various states of the gas with pressure on the y-axis and volume on the x-axis. So a PV diagram shows where a gas might be in a particular state and then transitions to other states. So this one, for example, shows a gas in state 1 that then transitions to state 2. It lowers pressure without changing volume. And then it transitions from state 2 to state 3 by not changing pressure while expanding. And there is a ton of information we can pull from this type of graph. In fact, using PV equals nRT, the graph gives us two of those things, P and V. So if we know temperature, we could figure out number of moles. If we know number of moles, we could figure out temperature. So for example, if T2 here was 300 degrees and the pressure is 2 kilopascals, how do we figure out the number of moles? Just plug it in, and here you go. We get 0.42 moles. Easy peasy. Now imagine that gas in state 1. It's a sealed container, the gas has a particular volume, and then we lock that volume in place so it can't expand or contract, and we drop the pressure. How could we drop the pressure of a gas when we're not letting it do any work and we're not doing any work on it? We have to cool it. We have to remove thermal energy from the system in the form of heat. Doesn't that make sense? The gas is going to get cooler, the temperature is going to drop. Do keep in mind that temperature and heat are not interchangeable words. Heat is the exchange of thermal energy. Temperature is a measure of the amount of thermal energy. So what would the temperature be in state 1 if in state 2 the temperature was 300 degrees Celsius? Well, convert that Celsius to Kelvin and then use the ideal gas law or the universal gas law or Boyle's law or Charles's law, or whichever one you think applies best. Plug in and solve, we get 2000 Kelvin. And then you can do the exact same thing again for point 3 and you'll get 1146 Kelvin. And there you have it. We have P, V, and T for every single one of these points. So why did the temperature increase from state 2 to state 3? Well, if you think about it, you're expanding the gas, but you're not decreasing pressure. Pressure is staying the same. In order for that to happen, when you expand the gas, the pressure wants to drop. The pressure is the ricocheting of the atoms and molecules inside the container, ricocheting off the walls. So the pressure wants to drop as you expand it. They've got more room to play. The only way that they can ricochet off more area with the same pressure is if they're moving faster, if they have more kinetic energy, if they're at a higher temperature. You have to add heat to the cylinder as it expands. In this case, you would have to add heat very carefully so that that line stays perfectly horizontal. Perfectly horizontal lines in PV diagrams are pretty unrealistic. Perfectly vertical is easy. Lock the volume in place with a key or a lock or something, and then add or remove heat to change the pressure? Easy. Perfectly horizontal lines are pretty unrealistic, although we certainly will make use of them sometimes because, well, they're easy. On that horizontal line process from state 2 to state 3, how much heat did we actually add? Well, you can figure out how much work was done using W equals minus P delta V. Plug in your numbers, you get minus 2,000 joules of work. Remember, it's expanding, so that work is negative. It's removing energy from the gas. But what was the change in internal energy of the gas? Here's that thing you have to memorize again. U equals 3/2 nRT. If you plug in U equals 3/2 nRT for state 2, and you do it again for state 3, and you subtract, you end up with 4,429 joules. So it gained 4,429 joules of internal energy while doing 2,000 joules of work, which means that we had to have added 6,429 joules of energy in the form of heat in order for that to work. Right? Doesn't that make sense? Conservation of energy applied to a gas. Well, it turns out that conservation of energy applied to a gas is known as the first law of thermodynamics. And the first law of thermodynamics says exactly that. It says the change of internal energy of a gas has to equal the amount of heat added or removed plus the amount of work done by or on the gas. It says that the total energy has to be conserved. Delta U equals Q plus W. As a general rule, we find work by finding the area underneath the PV curve. This is where those straight lines are handy, if not realistic. Just like we did in mechanics, where we oftentimes would ignore the curves and things and just go, that's approximately a triangle, things like that. So work is the area under the curve. Delta U is usually easy to find. If you know temperature and you know U is 3/2 nRT, just find the two U's and subtract to get the change in internal energy, delta U. And then once you have work and you have delta U, Q is typically found by then just plugging those in to the second law of thermodynamics, delta U equals Q plus W, solve for Q. Now, there are four major ways that you can transition from one state to another with a gas, okay? And those four ways all have names that you're gonna have to memorize, and you've gotta know some details about each and what they look like on a PV diagram. The first one is called an isothermal process. Iso means same, thermal, we're talking about temperature. Isothermal means a process that is at the same temperature. So if you expand a gas without changing its temperature, you have an isothermal process. It looks like this on a PV diagram. PV diagrams have something called isotherms on them. They have lines of the same temperature. And these lines are always concave up, and they sort of hug the axes when they get near them, and then they become smoother and rounder as you move further out. But oftentimes you can look at a glance on a PV diagram and say, oh, the point was here and now it's over there. That means that it must have a higher temperature just because it's further away from the origin. That's not always easy. If you have something that's near the y-axis and then near the x-axis, you might say, well, gee, does the isotherm do this or does it do this? Does it cut above or below those lines? That can be harder, but when you have something that's further away from the axis, it's very easy to figure out. It is not uncommon for the AP exam to ask you to draw an isothermal process, and when you do that, that line has to be concave up, so keep that in mind. Our next type of process is called an isochoric process or an isovolumetric process. You can probably guess what that means. There's no change in volume. That's like I said before, if you have your gas stuck in your cylinder and you then heat it up to change its pressure or you cool it to reduce its pressure, that would be an isovolumetric or isochoric process. An isovolumetric process is a straight vertical line on your PV diagram. What is the area under a vertical line? It's 0. So an isochoric process means there is no work done. The change in internal energy of your gas is going to equal the amount of heat that you added or removed because there was no work done. An isobaric process is a process that has no change in pressure. So if I took this and I heated it very gradually, it could push out against the atmosphere and expand. The pressure out here is still 1 atmosphere, right? And so as it expanded, as long as it was nice and slow, the pressure would be constant as it came out. You could get an isobaric process. Otherwise, they're pretty hard to do, especially hard to do quickly. But Either way, an isobaric process is no change in pressure, and so calculating work is super easy. It's minus P delta V, because your pressure is constant. You get this area under the curve is just a rectangle. Once you have work there, that's pretty simple to do. An isobaric expansion requires that you add heat. An isobaric compression requires that you remove heat. As a general rule, if I try and compress this thing, I'm going to try and that's going to increase the pressure. In order to keep that pressure from increasing, I've got to cool it down. And you would have to very carefully cool it at the same rate that you were pushing it in and trying to increase that pressure in order to keep the pressure to be the same. And the reverse is true with expansion. Finally, we have what's called an adiabatic process. The definition of an adiabatic process is one where there is no heat exchanged with the environment. There are two ways to do that. One's a little more realistic than the other when it comes to real engines. The less realistic way is to just insulate the heck out of this thing. Just cover it in so much insulation that as it expands or it contracts, it can't absorb or remove heat from the environment. That's pretty hard to do. A more likely way that adiabatic happens is just fast. Heat transfer takes time. And if you do something really fast, there's not enough time for heat to exchange. And that's a very common type of adiabatic process. That first type, the really unrealistic kind, where you just cover it in insulation and then you do it extremely slowly, that adiabatic process is also reversible. It's like you're adding an infinitesimal force every infinitesimal piece of a second, or you're removing a little bit of force either way to get it to expand or contract to make a completely reversible process. An adiabatic process that is also completely reversible is called an isentropic process, which means there is no change in entropy. Entropy is an interesting topic that we'll come to in another video. So I've got a really useful chart for you. Here it is. This chart shows you how to find delta U, Q, and W for these various processes, keeping in mind that areas under curves that are actual curves is calculus, so it's something that's outside the bounds of this class. So delta U is 3/2 NR delta T. Every time. Look down the chart, that's true for all of them except for isothermal, where by definition delta T is 0. Skipping over to work, for isobaric you've got minus P delta V. For an isobaric process, for an isovolumetric you've got 0, right? For the others, well, for an isothermal process you have this minus nRT natural log of final volume over initial volume. That comes from calculus, and we're not going to get into where that comes from. You're not going to have that memorized either. If you need it, you can look it up in the book for a problem set problem. It's not going to come up on the AP exam as something that you have to know. For Q, you have 5/2 nRT for isobaric. Well, if you look at it, PV equals nRT, delta U is 3/2 nRT, and you have delta U equals Q plus W. Q better be 5/2 nRT. And then for each of the others, everything we haven't talked about yet, you're just going to plug into the second law of thermodynamics. Once you know 2 out of the 3, use delta U equals Q plus W to find the third. And that's where this whole chart comes from. Speaking of natural logs and Euler's number are really fascinating topics, and the coolest equation in all of physics is e to the I pi plus 1 equals 0. That's a really neat equation that has nothing to do with this class. It's just super fun. If you want to kind of blow your mind a little bit about math, I've linked down below and in the card up above to a 3 blue 1 brown video about Euler's number and the relationship of E and I and pi and this really, really cool equation. It's way over the heads of high school students pretty much, but it is fun to watch if you're interested in math on a deeper level.